Okay, so now this is what a schematic diagram of an Hartnell governor here. Okay. So it consists of a spring. So spring is placed with concentric with the spindle. So this is what a spindle. So now sleeve has again two positions, upper position and lower positions. Upper positions and lower positions. Okay. So it consists of two bell crank levers. Bell crank levers. So bell crank levers are placed with mass. That is what ball. Okay. So this is what ball here. So you just observe the distances here. You are going to get a two type distance. That is what one is vertical length of bell crank lever and horizontal length of the bell crank lever. So again, function is same. So as variation of speed takes place, so the equilibrium position is controlled with the help of spring force here. Equilibrium position is controlled with the help of spring force. Again, so equation is obtained based on two conditions. One is the graphical method, and another one is analytical method. One is graphical method, another one is analytical method. So now let us consider the centrifugal force Fc is obtained as m r omega square, m r omega square, and it has a mass. It has a mass. That's what small mg, and it has a spring force. That is what Fs. Fs is spring force. Fs is spring force. Again, consider a small f. This is what a frictional force. This is what frictional force. Now analysis is done again considering a pivot point here and resolving the forces in horizontal direction as well as vertical direction and equating for zero. Equated to for zero to get the governor in equilibrium condition. Governor in equilibrium condition. So now let us note down. Let us note down. F is centrifugal force. F is centrifugal force. It is calculated as mr omega square. So Fs is spring force. Fs is spring force. Small f is frictional force. Small f is frictional force. Now let us draw the force position diagram or vector diagram with respect to the fulcrum of a lever here. With respect to the fulcrum of a bell crank lever. So now let us take position at a radius equal to r1. At radius equal to r1. At radius equal to r1. Now for equilibrium condition, so the bell crank lever should be in a right angled position. So then only we are going to get a constant speed. Then we are going to get a constant speed. If the variation of speed is there, you are going to get a displaced position of the bell crank lever. Okay? Displaced position of the bell crank lever. So let us take R1 is the radius of rotation of the ball for minimum speed. For minimum speed. Okay? So vertical distance is what? It is a. Vertical distance is A. Horizontal distance is B. Horizontal distance is B. Okay. Now, as inclination takes place, so the vertical distance is going to be tilted for an angle of theta 1 or oscillated for an angle of theta 1. Now this vertical distance of inclined position is what? A1. Similarly, so this position horizontal, it will become B1. It will become B1. Now, the forces which are acting at a different points, okay, different points. Now, at mass position, you are going to get two forces here. One is what? Centrifugal force, which is acting in an horizontal direction. Horizontal direction. So now this is what? M R1 omega square. M R1 omega square. Now the force which is acting at near sleeve position, at the end of this horizontal arm is what? Capital Mg plus Fs plus or minus F divided by 2. Okay. So now in this case, capital M is what? Mass of sleeve. Mass of sleeve. Okay. Right. Now, taking moment about point A, and equating it to 0 for equilibrium condition. So now let us go for first case. That is what? At radius R1 equal to so you are going to get centrifugal force F1 A1 is what? A moment of centrifugal force about the fulcrum A 1 by 2 in bracket capital Mg plus Fs1 plus F into B1. Okay. So just observe, centrifugal force is causing anticlockwise couple, mass of sleeve plus spring force as well as frictional force causing clockwise movement. Similarly, the mass and the acceleration due to gravity, okay, is what? A centrifugal force, gravitational force you are going to get here, it is what? M into Z, it is C1. So C1 into mg, it is causing clockwise movement, right? Now let us consider, this is what? Equation number 1. Similarly, for radius R2, now position of bell crank lever for R2, so this is what? Distance R2. Now let us consider, this is what? A mean radius R, or mean position of the bell crank lever R, and now this vertical distance is what? A2, okay, and this horizontal distance is what? B2, okay, and this distance is what? It is a C2. It is C2. Now again, if you consider the forces, so now you are going to get centrifugal force. This is what F2. Here you are going to get mass into acceleration due to gravity, and here you are going to get mg plus fs by 2, fs2, not fs by 2, fs2 plus f all divided by 2. Okay? All divided by 2. Now if you write the equation, equilibrium equation taking moment about the fulcrum point A, you are going to get F2 into A2 equal to 1 by 2 in bracket capital Mg plus Fs2 plus F into B2 here plus Mg into C2. Let us note on this as equation number 2. Let us note on this as equation number 2. Okay. In working range of the governor, if theta 2 and theta 1 are very small, then the distance A1 equal to A2 equal to A. Similarly, distance B1 equal to B2 equal to B, and distance C1 equal to C2 equal to 0. Distance C1 equal to C2 equal to 0. Then the possible position of the bell crank lever is what? It is of exact this position. Right? A1 equal to A2 equal to A, B1 equal to B2 equal to B. Suppose if you neglect the deflection of the fulcrum in vertical direction as theta 2 equal to 0, then you are going to get vertical position. Similarly, if you consider the theta 1 is equal to 0, this vertical position, this inclined position is going to become into vertical direction. Okay? Right? Now, if you rewrite these equations, above equations, that is what equation number 1 and 2, F1 equal to F1 into A is equal to 1 by 2 capital Mg plus Fs1 plus F into B. Other term gets 0 because C1 equal to C2 equal to 0. Because C1 equal to C2 equal to 0. So let us note on this is what equation number 3. This is what equation number 4. Now, subtracting equation 3 from 4. Subtracting equation 3 from 4. So let us note on what we are going to get. F2 minus F1 into A equal to 1 by 2 Fs2 minus Fs1 into B. You just check it. mg plus fs2 plus f. If you subtract, you are going to get two terms. mg get cancels, ff get cancels. You are going to retain the term fs2 minus fs1. fs2 minus fs1. So let us notify this equation as a fifth one. Okay? Let us notify this equation as a fifth. Now, so now spring has a stiffness. Spring has a stiffness or it has a spring rate. Okay. So let us consider S equal to stiffness of the spring Now H1 equal to movement of the sleeve. H1 equal to movement of the sleeve. Now, as difference of springs force is there, difference of spring force, that is what fs2 minus fs1 is equal to the product of movement of the sleeve and stiffness of the spring. Okay? That is what. So how much distance is going to move or compress? If you multiply with that one, spring stiffness of the spring or rate of spring, you are going to get a difference in force. You are going to get difference in force. So now spring stiffness is what? It is Newton per mm. Okay? Unit is Newton per mm. Now fs2 minus fs1 is equal to h1 into s. h1 into s. Now if you substitute in our equation, this is what fs2 minus fs1 equal to h1s equal to 2a divided by b in bracket f2 minus f1. So I'm just rewriting equation number 5 and equating for of spring stiffness but height of this sleeve, that is what, from lower position to higher position, it is what h1. So this can be obtained as theta into b. This is also equal to r2 minus r1 divided by a into b. So just note down. Draw one more figure here. So this is the main position of the bell crank lever. Now this is what the position of the lever for minimum speed. Now this is what position of the lever for maximum speed. Now, if you consider the axis of rotation, this is what R1, this is what R2. Now, total angle subtended by this lever is here, it is a theta. Here it is a theta. Similarly, angle you are going to get here, it is a theta. Okay? But the movement of the sleeve from minimum radius to maximum radius, let us take it as what? Moment of the sleeve. Okay? Right? So now based on this one, trigonometric relations, you can find out H1 equal to what? H1 equal to theta into B. H1 equal to what? Theta into B. So this theta is same for both the position. So this theta can be obtained as R2 minus R1 divided by A. So now H1 equal to R2 minus R1 divided by A into B. Now substitute value of H1 in this equation. Substitute value of H1 above equation. So what will get? So again, if you simplify this one further, what will get? 2a by b square in bracket f2 minus f1 divided by r2 minus r1. So now this equation gives the stiffness of spring, or spring rate, Okay? So you please remember this equation. Stiffness of spring S equal to 2a by b whole square f2 minus f1 r2 minus r1. Have you noted equation? Someone say yes or no.
Yes, sir.
You note down this equation, okay, and the previous these two equations, this one and this one. Okay, not done. In Hartnell governor, the extreme radii of rotation of the balls are 40 mm and 60 mm. And the corresponding speeds are 210 rpm and 230 rpm. Full point. The mass of each ball is 5 kg. Full point. The length of the ball and sleeve arms are equal. Determine the initial compression and the constant of the central spring. So just note down what are the given data they have provided. So R1 is given, it is 40 mm. R2 is given, it is 60 mm. Speed N1 is given 210 rpm. Speed 2 is given, it is 230 rpm. And mass of ball small m is 5 kg. Mass of ball is 5 kg. You need to determine what is the initial compression and constant of the spring H1 and S. You need to find out value of H1 and S. Clear. Now let us go for first find out constant of the central spring. That's what. Yes. Okay. So now let us go for first spring constant. Spring constant. So what is the equation to find out the spring constant? S equal to 2 in bracket a by b square in bracket f2 minus f1 divided by r2 minus r1. f2 minus f1 divided by r2 minus r1. Now f1 equal to what? It is a centrifugal force at radius r1 equal to
M R1 omega
40.
square.
Pardon?
M R1 omega square.
Okay, now let us find out m r1 omega 1 square. Right? M is 5 kg, r1 is 40 divided by 1000. Okay, substitute in terms of meter. So omega is what? It is a 2 pi n by 60. 2 pi n is how much? N1 is
210.
210 divided by 60 square. So now you find out what is the value of f1 here.
43.98.
How much?
43.98.
You get more. Check it. What is the omega value? 2 pi n by 60.
21.99.
21 point.
99. Plus
Right. Okay. Now
483.56.
in 483 no.
Omega square, sir.
Omega square. ಇಲ್ಲಿ ಬರೀತೀನಿ ನೋಡಿ ನಮ್ಮ equation. Check mark. M ಅಂಗ್ರು 5 kg.
Yes, sir.
40 mm ಅದ 0.04 ಮೀಟರ್ ಆಗುತ್ತಾ?
Yes, sir.
ಇದೇನಾಯ್ತು 21.99 ಸ್ಕ್ವೇರ್ ಆಯ್ತು.
96.71.
How much?
96.71.
96.71.
712.
7172.
Okay, right? Now, similarly find out centrifugal force at radius of 160 mm. Okay. Now F2 equal to m r2 omega square. Okay.
Yes, sir.
5 into 60 divided by 1000 into omega 2 pi is a 230 divided by 60 square. Find out F2.
174.03, sir.
How much?
174.03. 03.
170.03.
174.03.
Okay. Now Substitute all values in spring constant. S equal to 2. As lengths are same, you can go for 1, 1. F2 is 174.03 minus F1 is how much? 96.71. R2 is 0.06. R1 is 0.04. So now you find out yes.
Seven 732.
How much?
7732, sir.
7 point
7732.
7732, sir.
ಅಷ್ಟು ಬರ್ತಾ
ಹಾ ಸರ್ 7732, sir.
32.
divided by, it is what, Newton per meter here, because
Yes, sir.
you substituted these two values in what?
Meter.
Meter. Okay, now if you want to get this one, 7732 divided by 1000. Somebody give the value.
7.732.
How much?
7.732.
7.732 Newton per mm. You check out these two conditions carefully. Okay, if you substitute values of radius in meter, you are going to get spring constant in Newton per meter here. If you substitute R1 R2 value in terms of mm, you are going to get spring constant in Newton per mm. You please take care of units. Okay? Next, they have asked to find out what is the initial compression. Next is what? You need to find out what is the initial compression. Okay. So now initial compression of the spring is obtained based on the spring force as well as spring stiffness. Now for case 1, when it is an initial means it is R1, F1 into A equal to 1 by 2 capital Mg plus Fs1 plus F into B. This is the equation you got for equilibrium condition, right? Now in this case, mass of sleeve is not given, right? Frictional force is not given. Let us substitute M equal to 0. Let us substitute capital M equal to 0.
Yes, sir.
F equal to 0. Now what will get equation? What equation you will get?
1 by 2 FSB. FS1B.
Let us write here. Now I'll simplify here. F1 A equal to Fs1 into B. Correct?
Yes, sir.
This term will 0, this term will be 0. Here it is what? 1 by 2. Correct now? Next.
Yes, sir.
As they have suggested, length are equal, A equal to B equal to 1. Then what will get? F1 equal to 1 by 2 into Fs1. Right?
Yes, sir.
Sorry, now. Now, Fs1 equal to 2 times of F1. Is it right? 2 times of F1. Now F1 already I calculated. F1 already you have calculated. How much F1 you got?
96.712.
96.71.
71. Okay. 96.71. Someone calculate and give the value.
193.42.
1. Right? This is what initial spring force. You won't get any mm, you will get a Newton. Sorry. Okay? You will get only Newton. Okay? Now, initial compression of the spring H1 equal to, okay, H1 equal to Fs1 divided by S. 193.41 divided by how much you got S? 7.732.
25.01.
25.01
01.
mm. Now this is what initial compression of the spring is how much?
25.01.
25.01 mm. Right? Is it clear?
Yes, sir.
Okay.
Yes, sir.
If possible, we'll go for one more class today evening at 6 o'clock. Do we have a class at 6 o'clock?
So data ಖಾಲಿ ಆಗಿದೆ ಸರ್.